doing? All right, so here we are. Here we are. Whatever. I'm not even going to say the date, but it is Valentine's Day. Wow. And we're this far into calculus, and guess what? We are finally learning the fundamentals, right? Which is usually you learn first, right? The fundamentals, but not us, not us. Well, we do things out of order, don't we? So the fundamental theorem of calculus, or as I like to abbreviate it, the FTOC. And now my pen doesn't work. What is wrong with technology today? Was there a solar flare or something? Yeah, they're glitchy today. Like, yeah, I'm getting okay. So I call it the FTOC, fundamental theorem of calculus. It was first proven by this guy here. This guy is Isaac Barrow. Look at his hair. They had luscious locks back then. But Isaac Barrow, believe it or not, was Isaac Newton's teacher. Can you imagine being Isaac Newton's teacher? The Battle of the Isaacs, right? The student kind of surpassed the teacher. But anyway, Isaac Barrow, you might think that the wheelbarrow is named after him, right? The wheelbarrow, but not the wheelbarrow. The wheelbarrow is not named after him. But if you've ever been to the moon, or if you ever plan on going to the moon, there is a crater on the moon that's named after Isaac Barrow. It's called the Barrow crater. It's a must-see if you ever go to the moon, right? So he's not good enough to have anything on planet Earth named after him, but on the moon, yeah, we'll name the crater after him. Now, when I say it's not the wheelbarrow, people are like, wheelbarrow? I thought it was wheelbarrow, right? How many of y'all thought that it was wheelbarrow? Okay, it's wheelbarrow, barrow. Okay, so you learned something, right? It's not a barrel, it's a barrow. Wheelbarrow. Yeah, not wheelbarrow, wheelbarrow. There is no wheelbarrow. No. Wheelbarrow is not a thing. Okay, unless you want to like take a barrel, you know, if you take a barrel and you put like an axle through it, you could use it as a wheel. That might be a barrel wheel instead of a wheelbarrow, right? Yeah, you'd have to take a wheel and turn it into a barrel to make a wheelbarrow. But anyway, here's what it says. There's two parts of it. The first part I've already kind of showed you. The first part is essentially, if you can find an antiderivative to a definite integral, you can evaluate it by plugging in the top minus plugging in the bottom. So if we have the integral from a to b of little f of x with respect to x, and we let big F be an antiderivative, not the antiderivative, an antiderivative, then I can evaluate it by plugging in the top, f of b, minus plugging in the bottom, f of a, okay? We've already done that. I've already shown that to you. So what this always gives us is the net change. Always gives us the net change or the net accumulation as well, either one. Okay, so that's the first part. And in some textbooks, they call that the second part. So just know that the fundamental theorem has two parts. This is one of the parts. I like to do this one first, okay? So how can we use it? Well, let's see. Example one. I have a definite integral from 1 to 3 of the quantity e to the x minus 3 with respect to x. Now, where do we write these intervals of integration, as we call them? Right? Angeli asked that. We can put them above or below, or we can put them, you know, just out in front. Yeah, we don't put them behind there. So the program that I use, I like to put them above and below because it gets them out of the way of the integrand. And remember, if you have more than one term in your integrand, you need to have parentheses around it. Okay, so fundamental theorem says, if I can find the antiderivative of this integrand, then I could evaluate the definite integral from 1 to 3 by plugging in the top minus plugging in the bottom. So let's see if we can do that. What is the antiderivative of e to the x? E to the x, boom, minus. What's the antiderivative of 3 with respect to x? 3x. Now, remember, we don't need plus c, but it's been a while since I showed you why, so let's go ahead and put the plus c, which we're not going to have to show in the future. If this were an indefinite integral without the 1 and 3 there, we would be done with the plus c at the end. Now we're going to evaluate it from 1 to 3. So this is always the intermediate step. You find the antiderivative and you put the evaluation set bar at the back. Now we read this as from 1 to 3, but when we evaluate it, we always do top minus bottom because that's right minus left. That's big minus small. These numbers don't always have to be in this order. You could actually integrate from 3 to 1, but you would still plug in the top minus plug in the bottom. So here we go. Plug in the top minus plug in the bottom. I recommend you get in the habit of doing that. Plug in the top, parentheses, minus plug in the bottom, because that negative sign in between there It's a sticking point sometimes. All right, so now we plug in, we get e to the third minus 3 times 3, which you can call 9, plus c, minus plug in a 1, e to the 1 minus 3 times 1 plus c. Now, it's a definite integral because it gives you a definite answer, and that definite answer is always the net accumulation of that function from left to right. If this were a free response, you could stop once the c's are gone, okay? But look what happens to the c's. If you clean it up, e cubed minus 9 plus c, and now we'll distribute minus e plus 3 minus c. And since those are the exact same c value, right? C in general is an unknown constant, but it's the exact same c value in both cases. So what would c minus c be? 0. It's nothing. So because they always cancel out to give you 0 pair, you don't have to write them on a definite integral. You will not lose points for not having the plus c way up at the top here. So get rid of the blue part, okay? And then you could stop here. This would be your answer on a free response, but we could keep going. Let's go e cubed minus e, and then I can combine my two numbers, right? Negative 9 plus 6 is minus 6. So this is an exact answer that gives us the net accumulation of this function from 1 to 3. Which, did we look at this the other day? The graph of it? I'm kind of having a deja vu. It might have been from the previous 22 years. I don't know. Well, let's graph the integrand. If I graph e to the x minus 3, remember the negative 3 moves the graph down 3 units. So there's the horizontal asymptote. And then the e to the x is exponential growth. The y-intercept would be what? E to the 0 is 1, 1 minus 3. It passes through negative 2. So it looks like this. This feels real familiar. Yeah. Yeah, I think we did it. So it would be the integral from 1, which if I plug in a 1, it's going to be right here. Here's x equals 1. It's going to give me a negative value because e to the first would be 2.7, and 2.7 minus 3 is a negative number, and then 3 would be over here. So this will not give us the area because what's happening is you do have this little negative piece right here, and then you have this positive piece above. So what the integral does is it evaluates it and it gives you a negative quantity. That is the magnitude of the area. And then it adds to it the positive quantity. And then it subtracts them, right? Or it combines them. So again, the integral, when you always use the definite integral, it gives you the net accumulation. And we said on Friday, if you weren't here, you can use the integral to help you find the area. Like if you wanted to paint this region, you would have to find the x-intercept and integrate from 1 to that value and make it positive, either by putting a negative out front or integrating backwards. And then you can integrate from that value to 3 and then add them together. Okay, so you can use the integral to find area. Similarly, if you were told what the area of the red and black regions were, if they were handed to you or you knew what they were, you can use those to find the integral. But now you would be in charge of assigning the negative value to the little red regions area. Okay, they're not the same, but they are closely related, right? All right, sweet. Let's keep going then a little bit faster. Let's look at this one. This is a definite integral. How do we know this one's a definite integral? What do we call those guys? Intervals of integration. Yeah, intervals of integration. This one is typically called the lower bound. The lower bound, and this one is called the upper bound. And it's always nice to kind of graph it and see what it is you're finding, but it's not necessary if you're trying to evaluate it. All that's necessary is, can you find the antiderivative of the integrand? Well, perhaps I can. What I'm going to see, though, is I have a constant multiple in the top. And so I'm going to do a little bit of restructuring. Constant multiples, you go to the front, right? The front of the integral is like the back of the truck. Okay. And now what I might do also, like if I didn't recognize this, what I might do in this case is also bring the quantity from the bottom to the top and get rid of the radical. So that would be to the negative 1/2 power. Now, the problem with that is I can't expand that, can I? I don't know how to expand something to a negative 1/2 power. So I'm kind of stuck right there. And so when I get stuck, I'm like, oh crap, well, maybe that's not the best version to recognize it in. So maybe I'll put it back like this. And now you're like, oh yeah, what's up, Mr. Derivative of what? Arc sine. Yeah. So the 2 goes along for the ride, and this becomes arc sine of x, or of course it could be inverse sine of x like this, either one. And it's a definite integral. So make sure if you're working straight down, you keep the intervals of integration intact. And then once you find the antiderivative, you write the intervals of integration on the back end here. Okay. If you want to go off to the side and work with the antiderivative only and not put the intervals of integration, that's fine. But when you work straight down, that's your project, remember. All right, now here's what I said on Friday too. You could bring the 2 in as part of each term. 2 arc sine of a half minus 2 arc sine of 0. That's fine. Nothing's going to stop you from doing that. But in general, what I like to do is leave constant multiples out front. It's just my preference. It kind of makes the terms a little bit lighter, but you do have to put parentheses, or I like to put the beefy bracket because it's a little bit more important to me. And now I'll plug in arc sine of 1/2 for x minus arc sine of 0. So that's the fundamental theorem of calculus right there. I found the antiderivative, plug in the top minus plug in the bottom. Free response, guess what? You're done, right? Free response, you're done. Multiple choice, we keep going. Arc sine of a half. Remember how we answer that? We ask ourselves, sine of what angle gives us a half? It's a unit circle angle. Sine is positive in quadrants 1 and 2. Root 2, it has to be an angle. So it'd be like pi somethings. Pi 6. Yeah, pi 6. Okay. Now, sine of pi 6 is a half. That's why it works. But sine of 5 pi 6 is also a half. But 5 pi 6 is in quadrant 2, and that's not in the principal value range of arc sine. So if you're not sure which angle to use, always go with the quadrant 1 angle, because all of the trig functions do have quadrant 1 angles in their range. Okay. Arc sine of 0. Sine of what is 0? 0, right. And pi also works, right? Sine of pi is 0, but pi is too far away. Oh, that's sad. Pi is too far away. I guess I'll just have to eat cake. So we get 2 pi 6, which is 1 pi thirds. And that's the answer. That number represents the net accumulation. It's not an angle in this case. It's just a number, 1 point something, right? All right. Does the calculator know that? Let's see. What's nice about being able to express something as a definite integral is because your calculator is a number crunching machine. And if you can set anything up as a definite integral, your calculator can evaluate it. Oh no, it's downloading the ROM. Okay, from the iCloud. It worked, good. So here's what we would do. If we didn't have our equation already in y1, that is the integrand equation, we could type it into y1 and recall it, but if you're only using it one time, you might just type it in directly to the home screen. So how do we get to the definite integral? Math 8, okay? From the home screen, oops, that's math, that's derivative, sorry. Math 9, my bad. Math 9. Let me write that, right? Math 9. So math 8 is the derivative. That's the derivative. And then math 9 is the integral. Now, if you don't remember math 8 and math 9, just know that if you hit alpha window also activates the F2 menu, which gives you a shortcut to some of your more common things. And so there you'll find the n derivative and the f and I and t, okay? It also has absolute value. It has your sigma notation, which we'll use later in the year. And then log base allows you to type in without using the change of base formula. But anyway, so I've got it. And now I'll just type it in as I see it, right? 0 to 1/2. And my integrand, I'll hit alpha y equals. Remember, I won't type it in the way I modified it. I'll type it in the original way. 2 over the square root of 1 minus x squared with respect to x, right? And you double check, triple check, and you type it in, and it gives you that. And now you type in what we got, pi divided by 3, and it's the same. Okay, pretty cool. We don't want to find definite integrals from the graphing screen, even though it shades it, it makes it kind of pretty. It takes too long. You can't use the value in sequence with another operation like multiply or divide by something else. You have to be in the right window. So there's a lot of finagling that goes in. But from the home screen, piece of cake. And I can store that if I needed to. All right, let's look at the next example. 1 to e squared of x to the negative first. Well, it looks like it's a power rule, doesn't it? It's in the form ax to the n. So if I can find the antiderivative, let's see, add 1 to -1 and get 0, and then divide by 0 or multiply by its reciprocal, right? Oh, crap. 1 over 0 is what? Infinity. It's like dividing by 0. It doesn't work. Oh, crap. Remember, this is the one time that the power rule fails. And who comes to the rescue in this case? You yourself do, right? Because you know that the antiderivative of 1 over x, which is another version of it, is the natural log of what? Absolutely, the absolute value of x, right? And we don't need the plus c, and we evaluate it from 1 to e squared. Okay. Now, what if you left the absolute values off in this particular problem? It's not an indefinite integral; it's a definite integral. Would you lose points in this problem? No. Why? What's positive? What's it? Yeah, the interval of integration is over positive numbers. Very good. But if your interval of integration had included a negative number and you forgot it, now it's going to be, consequential. So it's good to have it in there, right? Better to have it, not need it, than to need it, not have it. So this becomes the natural log of the absolute value of e squared minus the natural log of the absolute value of 1. And that's it. Plug in the top minus plug in the bottom. Free response, you're walking away a winner. Multiple choice, though, that's not going to be an answer, right? So how do we contend with the absolute values? How about we just take the absolute value, right? What's the absolute value of e squared? E squared. What's the absolute value of positive 1? 1, right. Now let's evaluate. What is the natural log of e squared? It's 2, right? Because this is the same as log base e of e squared, right? Log base b of b to the blob is blob. Or you could bring the 2 out front, and I'm doing this over here on my workbench, and call it 2 times the natural log of e. And of course, the natural log of e is 1. All right, so this becomes 2. And then what's the natural log of 1? 0. Good. And then 2 minus 0 is 2. Nice. Now that one we can clearly see very quickly what we're actually doing. We know what the graph of 1 over x looks like. Let's graph it and see what's happening here. 1 over x is a parent function. It has a vertical asymptote on the y-axis, horizontal on the x, and it's your hyperbola here that lives in quadrant 1 and 3. It's a rotated hyperbola. It's your reciprocal function, right? And we are finding the net accumulation from x equals 1, which might be here, to e squared, which is about 9-ish, right? Somewhere in there. And I'm finding the net accumulation from left to right. So I'm finding this. Now, in this case, can I call 2 not only the net accumulation, but can I call 2 the area of the region? Yes. Okay. It also equals the area because the y value, the function, is positive on the entire interval from 1 to e squared. Now, when we did this on number 1, we didn't do it on the calculator, but notice the positive region above the x-axis is larger than the negative region. So the net accumulation is still going to be positive, right? This answer down here is going to be a positive number. 27 minus 3 minus 6. That's going to be what? I don't know. It's still going to be positive, like 18, 19. But that doesn't equal the area, even though it's positive, because the graph wasn't entirely positive on the entire interval. So you got to be careful. Just because the integral gives you a positive number doesn't mean that that can also represent the area. Okay. But in this case, it do. Nice. Nice. You want to verify in the calculator? Let's try it. Math 9. Math 9, the integral from 0 to e squared, which is second ln to the 2th power. And then you could type it in if you want as x to the negative first. Right above the x squared button, you have the reciprocal button. Or you could type it in as 1 over x. Either one, with respect to x. Big bucks, no whammy. Give me a 2. It takes a while because it's working hard. Come on, come on. Uh-oh. Tolerance not met. What happened? I went 0 to 2. Oh, that's gonna be harder because what do we have at 0? A vertical asymptote. It's trying to find the area of this unbounded region, which we saw with the standard normal curve could be finite, right? Or could be infinite. Unbounded regions can still have finite area. But in this case, I broke the calculator. Yeah, so make sure you type it in correctly, right? Don't be a doofus like oh, there it is. Right, 2. All right, way to go, calculator. All right, so fundamental theorem of calculus part 1. You like it? I like it. If you can find an antiderivative, it sure beats using all those rectangles or trapezoids to approximate. All right, example 2. Evaluate each definite integral using any method you want, verifying the calculator. Okay. The integral from 1 to 2 of x squared minus 3. When it says any method, I guess it means any method, including the FTOC part 1. Can I find the antiderivative of x squared minus 3? Yes. So let's just use the FTOC. X squared becomes 1/3 x cubed. 3 becomes 3x. Do we need the plus c? Not in this case. So evaluated from 1 to 2. Make sure you have that on there. And now we'll plug in the top minus plug in the bottom. Parentheses minus parentheses. All right, when I plug in a 2, I get 2 cubed is 8 times 1/3. I get 8/3 minus 6. And I plug in the bottom and I get 1/3 minus 3. How's that looking for a free response answer?
Pretty darn good.
Pretty darn good, right? Pretty darn good. Like the Rams defense last night. Oh, yeah, it was sick, right? All right. All right. But let's go ahead and simplify. Now, when you simplify, you can add terms in any order, right? The associative property of addition. So rather than getting a common denominator in the first parentheses and the second, let's see if we can just add the fractions together first, because the fractions might work themselves out, or I might still be left with the fraction. 8/3 minus 1/3 is 7/3. Crap. But if that had been 8/3 plus 1/3, it would have been 9/3 or 3. It would have worked itself out. And now I'll do -6 minus -3. Careful, that is what? -6 plus 3, which is -3. Now I'll get a common denominator. I'll put it over 1 and multiply by tree over tree. And so now I get 7 minus 9, right? Which is -2/3. And there's the multiple choice answer. Can that represent the area? You should be laughing preposterously. Negative area. That's preposterous. Right. Negative area. No, you can't have negative area. All right. Letter B, it said using any method. Ooh, that 3. Guess what? I have a constant multiple. Get out of here. Go to the back of the truck in the front of the integral. And then the square root of x, I'm going to write as x to the 1/2, right? Will the power rule work here for the antiderivative? I think so. So here we go. 3 goes along for the ride, times, leave a little space. X to the 1/2 plus 1 is what? 3/2, right? And we either divide by 3/2, yucky, yucky, gross, gross, or multiply by its reciprocal, 2/3. And then we evaluate it from 1 to 4. Okay. So again, let's just label these constant multiples. I call this guy the rider. He's there in the beginning. He's going to be there in the end. And this 2/3 comes from the power rule. There's one other type of constant that we might have multiplied in the front, and it would be a correction. If it'd be antacid, right? If we ever generate an unwanted 5, we can put its reciprocal 1/5 in the front. All right, now we need to evaluate it. So here's what I'm going to do. I'm going to simplify my coefficients. 3 times 2/3 is 2. And then I might actually take another line to simplify it, because x to the 3/2 is a really nice way to work with the power rule. But if I'm evaluating, I may actually prefer it in the radical form. Maybe not, but I'm going to leave the 2 out front. So I'm going to have 2, and then I'm going to plug in the top, 4 to the 3/2 minus plug in the bottom, 1 to the 3/2. Now, question, could I stop on a free response up here on this green line? Could I stop here on a free response? Is that a numeric answer on this line? No, no. Scooby doesn't think that's a very serious question either. No, but once you use the fundamental theorem of calculus, could you stop on the line below on a free response? Yes, this is your free response stopping point. And again, you don't get bonus points for continuing. Multiple choice, though, we keep going. 4 to the 3/2. Remember, we want to go small before we go big. So 4 to the 1/2 first, which is square root of 4, or 2, and then 2 cubed is 8. And then 1 to any power, as long as it's a finite power, is 1. Okay. 8 minus 1, 7 times 2, 14. There you go. Now that's a positive integral. Is that by default then also the area of the region? Every time? No. But is it in this case? I think it is, because 3 times the square root of x just takes the graph of the square root of x and vertically stretches it by a factor of 3. There's the integrand. And we're integrating from 1 to 4. So there you go. It does represent the area. Hey, real quick review. If I were to approximate that area using trapezoids, would it be an over or under approximation? Under approximation, because the graph is what on the interval? Concave down. If you're not sure, remember you could draw it, and all you need to do is draw 2 subintervals. If it works for 2, it works for all of them. If you're asked that question, so that would be an under approximation because our function is concave down from 1 to 4. What if I approximated it using left endpoint, Riemann sums? Left endpoint Riemann sums would give me an under approximation as well, but now it's because the function is increasing on the interval from 1 to 4. Right? Rectangles have to do with increasing or decreasing. Rectangles, increasing, decreasing. Concave has no R in it. And of course, if I approximated it using right endpoint Riemann sums, that would be an over approximation because f is increasing on the interval. Okay, good. All right. Blah, 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 bless you. All right. Letter C. Integral from 0 to pi/4 of secant squared of x. Do we know the antiderivative of secant squared? We do. What is it? Tangent of x. Do we need the plus c? Nope. We go from 0 to 4. Okay. Now, because it's a single term, if you want to do plug in the top minus plug in the bottom, you can. That's really more important if you have multiple terms. Okay. But yeah. Oh, yeah. I was going to say the 4 doesn't seem to work out. Pi/4. Más mejor que bueno. So we get tangent of the top minus tangent of the bottom. Free response. I'm walking away winner. Oh, yeah. Give me my points. Multiple choice. You're like, oh, yeah, it's unit circle time. Everybody's favorite time. Tangent of pi/4 is 1. Tangent of 0 is 0. 1 minus 0 is 1. There you go. So, yeah, this could be like your jersey number. If your jersey number is 1, put that on the back instead. Oh, it is the loneliest number. Right. Unless you don't like people. Yeah. No. All right, letter D. Letter D. The definite integral from 0 to 2 of the absolute value of 2x minus 1. Now, the calculator can handle this very, very easy. In fact, let's do it on the calculator first. All right. Assuming the calculator is allowed, yeah, why not, right? So here we go. Math 9 from 0 to 2. And how do we get the absolute values? Math number 1. Math number 1. Or you could do alpha window number 1, right? But that's not as good of a cheer. Alpha window 1. What? Alpha window 1. I like math number 1. Math, click to the right, number 1, and then 2x minus 1 with respect to x. Double check, triple check, boom, hit it. Oh, it's 2.5. Okay, 2.5. Easy, easy squeezy lemon peasy sneezy. All right, or 5/2. Hey, it's also 5/2. Yeah, thank you. Yeah, I knew that. But what if we didn't have the calculator? Can we find the antiderivative of 2x minus 1? Well, we can find the antiderivative of 2x minus 1, right? It's x squared minus x, but is the antiderivative of the absolute value of 2x minus 1 just the absolute value of x squared minus x? No, no, no. So, golly, we're hamstrung. We really can't do anything except this. Watch this. Here's an identity that we might be using throughout the year. The absolute value of x, it's not a trig identity, is the same as the square root of x squared in that order. You have to square it first, which takes any negative that might be there and makes it positive, and then you cut it back down to size by taking the square root of it. So maybe if I rewrite this as, let's see, the square root of 2x minus 1 squared, maybe that'll help. Does it? I mean, I can get rid of the squared by expanding that, right? Let's see what that would look like. Remember how to square a binomial? Ethan, you remember the quick little ditty? By the way, Ethan wrestled his way to the state final, so congratulations. Okay, well, regional, yeah. But I mean, you're gonna, according to you, you're gonna make it because you can finish like 4th and still make it, right?
Yeah.
But you're gonna finish maybe 1st and make it, right? Square, multiply, double, square. That's what I'm looking for. Square, multiply, double, square. Square, multiply, double, square. Square the first. 2x quantity squared is 4x squared. Multiply those two to get negative 2x and double it to get negative 4x. And then square the last. Negative 1 quantity squared is positive 1. Square, multiply, double, square. Square, multiply, double, square. Now, does that help me? Can I find the antiderivative of that? It's all to the 1/2 power. I can't really expand anything to the, no, now I'm gerstucken, right? There's a German word for getting stuck, which, oh, by the way, what do you call, what's the word for constipation in Germany? I learned it this morning. Fire from pooping. All right, fire from pooping. All right, we're stuck. We're stuck. Hey, speaking of Germany, on this day in 1939, the high-tech warship, the Lusitania, was built in Hamburg. Yeah, the Germans built it. Yeah, Hitler thought it was going to help him take over the world, but Hitler. All right, so here's the deal. We can't do it by using the fundamental theorem of calculus. So I'm going to take this work, and I'm not going to erase it. I'm just going to see if I can make it smaller, package it up, and put it off to the side. All right. So if I can't do it using the fundamental theorem, what's another way to do it? Well, how are you going to check? You don't have a calculator. Hey, I could maybe like try to identify the region and approximate it, but it's asking for the exact value. So if I was to approximate it, I would have to use like 1,000 rectangles, right? But maybe I can identify the region. Let's go off to the side and look at the integrand. Y equals the absolute value of 2x minus 1. Do I know what that looks like? The answer is yes. Yes, we should. Because your parent function is the absolute value of x, which we all know is your V for victory graph, right? It looks like this. It comes in, it's the slope of -1 on the left, +1 on the right. Okay. The derivative at 0 is undefined. It's continuous but not differentiable at the origin. If I could put this into standard transformation form, I could figure out where it lives. So I could factor a +2 out of the absolute values, and that leaves me x minus 1/2. Okay, I know what that does, right? Y'all know what it does? What does the 2 do to any graph, including this? Stretches it vertically by a factor of 2. So now the slope is -2, +2. And what does the minus 1/2 do? Is it down if it's on the inside? To the right. Yeah. So there's 1/2. And this slope to the left is -2, and the slope to the right is +2. So just a quick review. What would be the derivative at 3? 2. What would be the derivative at 0? -2. What would be the derivative at -5? -2. Right. What would be the derivative at 1? 2. What would be the derivative at 1/2? Undefined, DNE, right? So remember, because it's made up of two lines, the slope, which is the derivative, is the same. So anywhere to the left of a half, the derivative is -2. Anywhere to the right of a half, the derivative is 2. And at 1/2, the derivative is DNE. So if you were asked to find the derivative of this function at a point, you would do it this way also as well. But now we're trying to find the integral, which we know is the net accumulation. So let's see if we can identify the region from 0 to 2. Okay, here's 0. Bless you. And let's see, here's 2 right here. Hey, I don't have to use Riemann sums because guess what? My two shapes are perfect what? Triangles. Yeah, so I can find the exact value by finding the area and helping me by adding them together. So let's go ahead and do that. Let's do these in little small pieces. The area of the small one is 1/2 base times height. We'll call it a sub 1. What's the base from 0 to 1/2? 1/2. And what's the height? Well, it's the function value at 0. What is that? You plug in a 0 for x and you get 0 minus 1 is -1. The absolute value of -1 is 1, right? So that ends up being 1/4. Now, if there were room, I would write it in there, but there's not. So I'm going to do this. I'm going to write it and draw an arrow to it. And now the big one, a sub 2. Again, it's 1/2 the base times the height. What's the base from 1/2 to 2? 3/2, right? 1.5, 1.5. Again, it's easier to work with non-decimals, fractions when you don't have a calculator, but 1.5 will work. And then the height would be the function value at 2, which if you plug it in, 2 times 2 is 4. 4 minus 1 is 3. Absolute value of 3 is 3. So now we multiply straight across and we get 9/4. Is that what you said?
I think the mask muffled what I.
Oh, yeah, the math. It is so good at keeping COVID out and correct answers also from getting out, or COVID from getting in, correct answers from getting out. Nice. 9/4. And there was room to write it in there. Okay. Now, because both of these regions are positive, the area is going to be the same as the net accumulation. So if you were to do this on a free response, that is, if this were a free response, you would show your work here. And by having these numbers, 1/4 and 9/4 written in those regions, if you showed what you were doing with those numbers back in your project underneath the integral, that would be enough to indicate your method. So let's do that. The integral would be 1/4 plus 9/4. And again, they're both positive because we're integrating from left to right and they're above the x-axis. Yes, yes. All right, now in a free response, you could stop right there and you would get full credit. We would look at that and say 1/4, where in the heck did that come from? Oh, look down there, there it is. It's the area of the region. 9/4, oh, there it is. So when you calculate something, make sure it shows up in your calculations. Now we'll just add them together. We get 10/4, which is 5/2, which is 2.5. Yeah. Life is good, right? Yeah. We did that with the calculator. We got the same answer as the calculator. So the calculator is as smart as we are. Very good. Don't say us. It's not as smart as us. It's as smart as we are. Or just as smart as we, which kind of sounds silly, but it's correct. Yeah. All right. Yeah, all of this over here was workbench work. Yeah. Getting a standard transformation form, sketching the graph, finding the areas, and then I bring it back over here to my project, and notice I'm working straight down without equal signs, all equal. All right, so just remember that when you have absolute values of linear functions, you're going to probably want to graph them, whether it's a derivative or an integral question. All right, let's look at example 3. Find the whoa, I know, right? Find the exact value of this. It says to find the exact value. 1/2 to 1 over e of this. Now, when you look at the elephant at one time and you're like, I have to eat that, you almost choke without even taking a bite. But if you take one bite at a time, that's how you eat the elephant, right? One bite at a time. So let's look at it in pieces. The good news is that it's 3 separate terms. And I can treat individual terms as individual problems. In fact, you could give them each their own integral and their own dx if you wanted to, all right? Or you could just think of it as 3 terms with their own integral, because that's a lot of writing. Here's what I mean by that. You could actually go ahead and as you go through, pull constant multiples out front. So you could write this as 10 times the integral from 1/2 to 1 over e of x to the 4th dx. You would need the dx. Minus 2 times the integral of, now that little function, I think I'm going to rewrite it as 1 over the square root of 1 minus x squared. And y'all know why. Dx. And then minus 5, you go out front, the integral from 1 to 1 over e of 1 over x dx, instead of writing it as 1 over x. You could actually do that. The problem with doing that, though, is if you accidentally leave off one of those interior dx's, you'd lose a point. Because now, well, as long as it doesn't change the problem. If you left the last one off, you probably would not lose a point because nothing follows it. But if you left one of the interior ones off, like let's say you left the middle one off, now mathematically you're saying that this whole thing is the integrand. Okay. And so that's not good. So yeah, they don't take off usually for little things like that unless it changes the problem. And that does. So I wouldn't recommend doing that, but you certainly can. You do want to go through though and mentally think about rewriting individual terms if you need to. Yes, Mason. Yeah, I forgot this right here, the 1/2. Oops. Yep. See, that's why it's a lot of writing. I missed that. Yeah. And then the 1/2. Yeah, there you go. It's a lot. It's a lot to think. So here's what I would rather do. I would just rather say, okay, I think I can do this. I think I can go straight through. I'll just focus on each term at a time instead of rewriting it. So here I go. The 10 goes along for the ride in the first term, leave a little space, x to the 4th becomes x to the 5th times 1/5 out front. Boom. There's my first term. No big deal. I got it. Second term. All right. Minus 2, you go along for the ride. Oh, that's the same as 1 over the square root of 1 minus x squared, which is the derivative of, again, arc sine of x. Good. Okay, I got that. And then the next term, it's minus 5 over x. Well, that's just minus 5 times the natural log of the absolute value of x. Boom. See? So if you can compartmentalize those in your head, it saves a lot of writing and a lot of potential careless mistakes where you'd lose points, like I would have, you know. And then you evaluate the whole thing from 1 to e, which is going to be a little bit easier to evaluate than doing each one from those intervals. So now plug in the top, right? Minus plug in the bottom. All right, now it said to find the exact value, so I'm not really interested in simplifying. So this is just an exercise in, I don't know, transcription. 10 times 1/5 times 1 over e to the 5th. Okay, I'm just going to write it as 1 over e to the 5th. Boom. Right? Looks good to me. And now minus 2 arc sine of 1 over e. Okay, I can do that. And then minus, I need more space here, right? Minus 5, the natural log of the absolute value of 1 over e, which if you forgot the absolute values there, you wouldn't lose points because 1 over e is already positive. All right, so there's the first term. Yabba dabba do. I will now do the second term. Plug in the bottom, 1/2. So I get 10 times 1/5 times 1/2 all to the 5th power. Good. Minus arc sine of 1/2. Yes, yes. Minus 5 times the natural log of the absolute value of 1/2. I could drop the absolute values, but I'm just going to leave them in there. And you know what? That's the answer. Hip, hip, hooray. Hip, hip, hooray. Now, can some of those terms be simplified? Yeah, certainly. Yes. Yeah.
Did your class do this though?
Oh, I don't know. You want to go around and ask them? I think so. Do you have her name?
No, we don't have those.
Who got bikes? Raise your hand if you got your kid a bike. Let's look at that girl. See if Brody's go show Brody over there. All right. The things that I would think about simplifying, look at the natural log of 1 over e. Oh, I did? Oh, yep, I sure did. Thank you. See, it was an activity in transcription and I messed it up. Was that your girl, Brody? Yeah, okay. All right. So anyway, let's look at this right here. If I look at -5 natural log of 1 over e, I don't need the absolute values because it's positive. That's e to the negative first. What could I do with that? I could bring the -1 out front and call that -5 times -1, which makes it +5 natural log of e. And then, oh, what's the natural log of e? 1. So that term could become a +5. Okay. You don't have to do that. This is just going above and beyond. And then the other thing that we could probably simplify is this term here, -2 arc sine of a half. What did we say arc sine of a half was? Sine of what angle gives you a half? Pi over 6. And so this term could become -2 pi 6 or -1 pi thirds. Yeah, and that's about the only thing that simplifies down to something. What's that? Oh yeah, you certainly combine the numbers. Right. But those are the two things that I think are worth reviewing. Okay. So that's a good place to stop because now we're going to look at areas, and this section is pretty long, but not as long as the next section. The next two sections, this one, what's left, and 4.4, I would consider probably the two most important sections all year. Okay, absolutely the two most important sections all year. So anyway, we'll stop right there. I will put your 5 questions into AP Classroom for you to start beginning 4:30 in the morning.